With the centralized control plane, we see the potential of a higher flexibility of controlling traffic flows. But what comes with the flexibility is also the complexity. Okay, the complexity of computing these flow table entries as well as manipulating the flow table entries. So you see there's quite a bit of challenge ahead in order to drawing the talents to help us address the challenge. Okay, the design of the control plane in SDN is also this, very open. So we are open about the architecture of the control plane as well as the implementation of the control plane. So that it's easy to contribute code, to integrate these contributed code into the existing module. To contrast, in the traditional router, which takes the per router approach there, we do the route computation as well as packet forwarding, all inside the router. So the router there is very specialized. Okay, the switching hardware for packet forwarding, very proprietary. The implementation of the routing protocols, also proprietary. Okay, what's worse is that connecting the hardware and the routing protocols, there's also a proprietary closed router OS. For example, Cisco has its own OS, which coincidentally is also called iOS. Okay. Now you see, when the user demand gets higher, okay, or diverse, okay, it's very hard to add functions into such a very specialized hardware, okay, with lots of these proprietary design, proprietary implementation. As a result, we have lots of these network equipment manufacturers out there, okay, making different, okay, physical boxes, okay, each performing some sort of networking functionality, network layer functionality, such as firewalls, net boxes, okay, and these days quite popular, okay, especially for the data centers, okay, or service providers, load balancers. Okay. So this, okay, continues on until about 2005, 2006. That is when the global economy is really well, doing really well. Okay, so due to the economic activity, okay, the user demand is super high. Okay, and that is also the time people begin to discover that, hey, the internet, okay, the application domain goes really fast. Okay, that's drawing a lot of real user demand. The physical layer as well as the link layer technology is also growing, evolving really fast, so that it makes the network access also really fast. But we are actually stuck, okay, in the middle, the network layer of the internet. Okay, so this is also known as the hourglass model, okay, where the application layer, the higher layer protocols, okay, people actually design all sorts of things. It gets diversified, okay, and below, okay, in the link layer, physical layers, okay, lots of innovation is also happening there, okay. But the ways there, the IP layer, the network layer remains really thin, okay, and that gives you this hourglass shape. In 2005, 2006, that is about the time people begin to find that, hey, that hourglass model there, it's been working, that is great, we appreciate that, but that very narrow ways is probably now choking the development, okay, the expansion of the lower layers as well as higher layers further. Okay. That's why SDN shows up, and the attempt, okay, the idea is essentially to expand, okay, well, to make the internet's very narrow ways, okay, a bit wider. So the change of the router architecture going from more proprietary and closed to more open and extensible is very similar to this change we see in the PC industry, from the mainframe, gigantic warehouse-sized computers such as this one we're seeing on the slide. Okay, so this is a mainframe computer. It runs specialized hardware, specialized operating system, and specialized applications. The industry was really small, okay, and computer very expensive, and it's super hard for the programmers to get their hands on one of these machines. And quickly we know that this is not going to satisfy the human need. And there comes the personal computer industry. Okay, so the main difference is this: we define this is the hardware layer, this is the operating system layer, and this is the application layer. And between the layers, we have these interfaces. Okay, and once we define the interfaces, we open it up so that it allows the hardware designers to use their creativity to diversify the hardware design, to come up with different hardwares for different purposes to connect to the system. We also allow the application programmers to come up with different application use, different implementations for the same use. Okay. Even in the operating system layer, we see today, right? There are multiple implementation, multiple designs of these operating systems. And one of them, for example, Linux here, is completely open source, which makes the computer system very open, general, and extensible. As a result, in the older time, in the mainframe computer, the industry is very small, innovation very slow, and this is due to the vertically integrated architecture. Everything is closed and proprietary. And nowadays, we have a huge industry, and there are still innovation going on, and it's going really, really fast. This is thanks to the very open interface, and very open logic, open mindset there. So it's also due to this, the horizontal separations of similar functions in the same layer. So application layer, operating system layer, and the hardware layer. Separations of the components and open interface connecting the components. SDN is definitely here to try to make the industry larger and the innovation faster. But you see that we want to be open as well as extensible. To allow that, we need to define clearly, what are the layers and what the interfaces are connecting the layers. So first, at the bottom, we do have the switch hardware, isn't it? So that is the generalized flow-based forwarding layer. And then we are at this interface connecting the data and the control plane. So that is the first interface. And then we come to the control plane. So this is the part managing, allowing communication between the higher level applications to the switching hardware. And the last one, the highest layer is the computation logics, including routing computation, including load balancing computation, including, for example, firewall computation or NAT translation. To go over the layers in more detail, and to draw it as one picture, so this is what you're seeing here. At the bottom, we do have the data plane, and this is the lowest layer, where we have the very fast and simple switching fabric. What it does is just to do forwarding, generalized forwarding real fast. And it's based on the flow table installed from the controller in the control plane. And that installation is enabled by the protocol, the interface defined here between the controller and the data plane. So that is the protocol allowing communication between the data plane to the controller. So essentially what's defined there is the set of APIs, allowing installing the flow table, changing the flow table. One layer up, it's the SDN controller. This is also known as the operating system of the router that connects the route computation part with the packet forwarding part. More specifically, inside the SDN controllers, the three major components are these. First, SDN controller maintains a huge database about this SDN network. So inside this SDN network, how many routers are, and what the IP addresses of these routers are, where they are, and how they're interconnected. So all sorts of information about the SDN network. Second component, it defines a set of these APIs allowing communication from the controller to the applications above, to the computation logics above. And those API are called the northbound API. Similarly, we also define a set of APIs allowing the controller to talk to the data plane, to talk to the switching fabrics. And those are called the southbound API. And you heard a bit about this, right? This is the open flow protocol in the previous slide. Lastly, the characteristic of the SDN controller is this. Okay, so this thing here is huge, okay, nowadays. A lot of times we run it not on just one machine, oftentimes multiple physical machines. This is so that we can make sure that it's more scalable as the network is growingly big. And we could also add some redundancy. Okay, so multiple machines runs multiple incidences of the component. Therefore, okay, we have some robustness into the system. Therefore, hey, in case one physical machine lost the router's information, there is another physical machine there storing a copy of it. Okay, so you see, for fault tolerance, robustness. At the top, we have the application layer. So we see routing algorithm, load balancing algorithms, all sorts of other algorithms allowing us to control the traffic flow will be there. Okay, so they are the brains of the control. Now, once the computation results are out, we use the northbound API. So this is the service provided from the lower layer, SDN controller. And these northbound APIs will be allowing the results being communicated down to the SDN controller. And from there, SDN controller using the southbound API to install the flow tables. So that is the functionality of the top layer. The characteristic is this: each of these computation logic, okay, is unbundled. They are not strictly provided by the router vendor. It could be contributed by the third party, completely open source.